Hi, and welcome to this video on numerical methods. And in previous videos we've talked about numerical methods for locating roots. In this video we're going to be talking about something called Trapezium Rule, which is used to find an approximation for the area under the curve. So we're going to deal with that first bold bullet point in this video, and then the other two bullet points, which are to do with issues surrounding Trapezium Rule, we will deal with in the next video. So here we go. So let's say you've got a bit of a horror show of a function that you're struggling to integrate. How can we do it using a numerical method to come up with an approximation for the area? Well, the first thing we're going to do is we're still working out the area in between limits b and a of our function f of x. And what we're going to do is we're going to divide it up into a number of equally spaced strips. And let's call the width of each strip h. Then what we're going to do is imagine drawing a line across the top of each of those strips by the curve. So we just can draw a straight line through here. And you'll see that what we get essentially are a series of trapeziums. But you'll notice from now on, like I said, this first one looks reasonably accurate. This one here, there's definitely a gap between the straight line and the curve. Likewise on this one, and particularly this one here. So that's why it's going to be an approximation, because some of these straight lines are going to be better approximations to the curve than others. What we're going to do now is just find out the area of each of those trapeziums and add them all together. So what we've got first of all is to work out the area of trapeziums, we need our parallel sides. So we're going to call those y0, y1, y2 all the way up in this case to y5. And therefore the area that we're after is going to be approximately equal to the sum of those trapeziums. And so that trapezium there is going to be half y0 plus y1 times by h, so half the sum of the parallel sides times by the distance between them. That's our formula for trapezium. The next one is going to be half y1 plus y2h, and then the next one, you can see what's happening here, and so on and so forth. And there you go. All I've got to do is that calculation there. Now, the problem is that thing there is a little bit of a mess. It's a bit of a big old beastie. So what we're going to do is try and do a bit of tidying up and see if we can make that a little bit easier. And the first thing to notice is that we can take out half h from each term, because that half h from our trapezium rule, from our formula for the area of trapezium is appearing in all of the bits there. So let's do that. So let's take out the half h, and when I do that, if I take half h out of this first bit here, I'm just left with y0 plus y1. Take half h out here, I'm left with y1 plus y2, and so on and so forth. And now if you have a look at what's going on with our values in here, you'll notice that the majority of lengths are being used twice, because y1 appears as a length for my first trapezium, that's this one here, and also my second trapezium here. So those being appeared twice, and then you've got only the first one and the last ones just appear the once. So let's just do a little bit of rewriting of that. So we're saying we've got half h there, our first and our last ones appearing once, and then two lots of each one of our other ones. And that there is essentially our basis for trapezium rule. We've done it with 5 trapeziums. Let's just now turn that into any number of trapeziums. So for an area with n equal strips, that thing there is trapezium rule. And it still doesn't look particularly nice, but it is actually quite nice and simple to use. And another way to think about it would be to say it's half h times by the ends, which are these two, plus 2 times all the middle strips, which are all those ones there. You also get this, you get given this in the formula booklet, and we've got a formal definition for what value we need to use for h, which is this thing that's here appeared here, b minus a over n, so the distance between there divided by how many strips. But I've got to be honest, in my experience, that's the red note I've put there. In my experience, it's just what I think. It's not a statement of fact, but you tend to find more mistakes get made by students trying to use that formula. As it turns out, 99 times out of 100 it'll be blatantly obvious what value you're going to be using for h, as we'll see in the examples that we're going to be coming up with. So I tend not to encourage my students to use this one. I tend to tell my students just to have a look at the information you're given and just use essentially a little bit of common sense. Okay, so that's the theory all sorted. Let's have a look at an example. So there we go. We've got to find the area under the curve y equals root sec between those two values, minus pi over 3 and pi over 3. And what you tend to find in exams is you'll be given a table, and normally you'll be given a table looking like that, and they will normally worked out some of the values for you and ask you to work out the remaining ones. We're going to have to do all the work here ourselves, so let's just start plugging numbers into a calculator, and we start getting our values for root sec x. There they go. And so now what we're going to do is put those values into our trapezium rule. Again, it's given in the formula booklet, this version here. I say I prefer to think about this one here, half h to the ends plus 2 times the middles. So off we go. Let's start off with half times h, and in the mark scheme there's always a first independent mark for putting that bit in, and we can see very clearly from the table, rather than needing the formula to work it out, we can see that the distance between there and there, the width of our first strip, or all our strips, is just pi over 6. So that's what I was saying earlier about it just being a bit obvious. Right, let's chuck in the ends. So that's those two, plus 2 times the middles, that's those 3, and then it's just a case of whack it all into a calculator, and there you go. There is an approximation for our area under the root sec x curve. Now, you can check what you're doing here, because your calculator, if you're using that calculator, will have an integral function on it. So if we just bang that into the integral function on our calculator, we see the actual area is 2.336. We got 2.389. So we can see the trapezium rule is giving a reasonable approximation. But we can improve on that, and in the next video we'll look at how we can get a better approximation and get much closer to the actual value. Let's have a look at an exam style question. So we've got 4 parts to do with this. We're dealing with the curve y equals 4 over e to the x plus 3 between those two values of x equals 1 and x equals 2. And again, there's our table, and you'll notice again, first question will be, okay, let's just put in some missing values. So part A, let's put in those missing values, chuck 1.25 into our formula, and nice easy marks on the exam. Making sure we give them to 5 decimal places. There you go, there's our 2 values. That's part A done and sorted. On we go. Use the trapezium rule to find an approximate value for the area of R. So again, off we go. First thing we need is h, but we can see that from the table our value for h is going to be 0.25. So we've got half 0.25. The ends, plus 2 times the middles. And again, what you'll find on the mark scheme is that you get the first mark is for that bit, second mark for getting the correct structure, and then the third mark generally tends to be for tidying it up and coming up with the right answer. So there we go, all nice and easy, just chucking numbers into a calculator. Part C, now depending on where you're coming at this, it might be you're doing this topic before you've done all the integrations, in which case you can just do this next part using the integral function on your calculator. Or alternatively, if you have done all your integrating work, all I'm going to do is go through it by using the substitution that's been suggested. This often happens in exam questions where you have to compare your approximation with what you get from the actual value. So here we go. Let's go for it using our substitution, which is u equals e to the x. du dx equals e to the x. Do the bit of rearranging to get it saying dx equals, because we're going to want to replace that dx with something in terms of du. There we go. Now let's do all the replacements of the limits. That's the next thing we've got to do. So we've got to change the limits so they're in terms of u. So when x equals 2, u equals e squared. X equals 1, u equals e. Plug all of that in. There we go. The final thing we've got to do is we've got to replace this e to the x here. But clearly that's just a substitution for u from that expression there. So let's do that. And just tidy it up a little bit. So there we go. So that's what we're looking at as our integral now. And we've got to integrate that thing. How are we going to do that? Well, let's rewrite our fraction using partial fractions. So off we go again. Let's do some partial fractions work on this. There's our format for partial fractions. Let's do all the working out. I'm going to whip through this fairly swiftly. So u equals 0, leading to a equals 4 over 3, u equals minus 3, leading to a value for b, which is going to be minus 4 over 3. So there we go. There's our integral written as 2 separate fractions. Again, write it as the 2 separate fractions within the integral. I've taken out 4 over 3 just to make life a little bit easier. Now we can do the integrating, and we're going to get lns from integrating 1 over u and 1 over u plus 3. Substitute in the limits, and the intention to subtract. There it is. So here we've got e squared subbed in. Take away what we get when we sub in just e. Now, what tidying up we do here? Well, this thing here, ln e squared, bring the 2 to the front using your log laws. That will give us 2 ln e, and ln e is just 1. So this thing here is just going to be 2. Likewise, this thing here is just going to be 1. So that makes life a little bit easier. There we go. And I've done the subtraction, so we've got take away 1 here. And notice this plus sign here comes from the minus, making that into a plus. And we want an exact value, so I'm going to tidy that up a little bit. I've got 2 take away 1. And then I've got plus e over 3, sorry, plus ln 3 e, try again, plus ln e plus 3 minus ln e squared plus 3. So I can write that as a single ln with the e plus 3 over the e squared plus 3. Hopefully you're keeping up with all of that. If you need to just pause the video and just work it through in your head, then please do. So there we go, there's our exact value. Right, that exact value is going to be required on part D. So finding the percentage error, so we've got our original estimate from Trapezium Rule, which was that, our actual value, which came from calculus, which was that thing there. To do the calculation about percentage error, we're going to need that as a decimal. So there it is, plug it into the calculator. Keep that on your calculator screen, you're going to need that, and keep that stored under A and S. Because now our percentage error is the difference between those two things. So that's our error, divided by what the actual value should be, so that's this one here. So again, using your A and S key for the bit on the bottom. And then it's a percentage error, so we've got to stick in a times by 100. That's all in your calculator. Press equals or execute, and there we go. So as it turns out, our estimate was only 0.05% away from our actual value. So that's a pretty good job done by Trapezium Rule. And there you go. So you've got a Trapezium Rule question mixed up with an integration by substitution and just an extra little bit of kind of mathematics to work out percentage error. And there you go, you're all done.